Hey, welcome back to Math with Patrick. Today is September 7th, and we're solving problem 250 from the Daily Epsilon calendar. And as with other problems in this calendar, the answer should match today's date. So I'm expecting that this x right here is going to be a 7. So we need to find the smallest natural number x such that this expression is a square number. So we need to find 10 factorial times x to be the same as some square number. I'll just do s for square number for now. A square number is just a number that you can get by doing another number times itself. So like the first few square numbers are like 1 times 1, 2 times 2, 3 times 3, 4 times 4, and so on. And other things like this factorial. A factorial is just taking all of the numbers starting at, in this case, 10, and multiplying them all the way down to 1, and you just kind of count down one by one by one. So this 10 factorial is the same as 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And the last thing is that a natural number is it's essentially like a whole number that's 1 or more. So actually, all of these are examples of natural numbers. Some non-examples are like -2 or 0 is a little bit iffy here. I like to say that it's not a natural number, and I like to say that it is a whole number. So like I've just circled a bunch of whole numbers, and now I just circled a bunch of natural numbers. And we just need to figure out what natural number works best for this x right here so that we get some kind of square number like that. And before we just solve it real quick, I do want to talk about a quick strategy where whenever we have a square number, let's just say 16, we can always write it as, well, a square number, like something times something, and I'm going to use this exponent 2 to show that, I'm doing something times something, like 4 times 4. If we pick a bigger square number, let's say 100, I could just do 10 squared. But if I wanted to maybe go further and find the prime factors instead of just a factor, I could for 100. I could call this like 2 times 5 times 2 times 5. Right, here's a 10, there's a 10. And the point of why I'm doing this is to show that I could also write this as 2 squared times 5 squared. Or this actually could have been 2 times 5 and then squared. The important thing here is that with the prime factorization of any square number, you're always going to have even exponents. All I really want to show is that once we find the prime factorization of 10 factorial times some number, we're just going to have all even exponents. So let me get that 10 times 9 times 8 all the way down to 1 on the screen again. And we should see what kind of exponents we get in our prime factorization. So this 10 is a 2 and a 5. This 9 is a 3 and a 3. This 8 is 2 times 2 times 2. 7 is prime. 6 is 2 times 3. 5 is prime. 4 is 2 times 2. And then 3 and 2 are primes. And then the 1 doesn't really matter for our prime factorization. So counting up all of my 2's, I have 1, 2, 3, 4, 5, 6, 7, 8 of them. So I could say 2 to the power of 8. Counting up the 3's, I have 1, 2, 3, 4 of them. Counting up the 5's, I have 2 of them. So that's 5 squared. And then counting up my 7's, I have just 1 of them. And then there isn't another prime number in this list because the next one would be 11, but that's not part of that 10 factorial. So now we have basically this condition already set where we have only even exponents in our prime factorization. The one thing is that we're missing a 7 because we have 7 to the power of 1, not 7 to the power of 2. So by tacking on another 7, we can have all even exponents, and we need the 7 here to get a square number. And we don't need to touch any of these to guarantee a square number. So this is our square number right here. It's whatever 10 factorial times 7 is. And I know it is a square number because it is 2 to the 4th times 3 squared times 5 times 7 all squared, whatever that is. Don't know these numbers, but I do know that it does check out. So there's my solution. Maybe you can figure out what these numbers are if you really want to, but I think I've solved the problem enough. So thanks for watching, and I'll see you tomorrow. Bye.